Hi everyone, welcome to the very first video on this channel. Today we are diving into a recent paper from Meta, presented at ECCV 2024, titled Sapiens: Foundation for Human Vision Models. This paper introduces a new approach to human-centric computer vision tasks. At its core, the Sapiens model builds on a vision transformer backbone, pre-trained on a large-scale dataset. By attaching task-specific heads, the model is fine-tuned for downstream tasks like human pose estimation, body part segmentation, depth estimation, and surface normal prediction. Let's break it down step by step. The first step is pre-training. The encoder is trained on humans 300M, a new dataset derived from a corpus of 1 billion in the wild images. Images with watermarks, text, or unnatural elements were removed, and an off-the-shelf person detector ensured only high-confidence human images were included. Specifically, images with at least one person detection with confidence score of at least 90% and bounding box dimensions exceeding 300 pixels were kept. The result is a dataset rich in human diversity, with most images containing more than one person, as shown in this pie chart. The pre-training follows a masked autoencoder approach with a masking ratio of 95%. Simply put, 95% of image patches are hidden, and the network learns to reconstruct the full image. Here you can see examples of the original, masked, and reconstructed images. The input image resolution is 1024 by 1024. 4 times higher than previous pre-trained vision models. This massive scale required 1024 NVIDIA A100 GPUs running for 18 days to train the largest variant, Sapiens 2B. Once pre-training is complete, task-specific heads are attached and the model is fine-tuned end-to-end using 1024 by 768 images. For pose estimation, Sapiens uses a top-down approach. A person detector first detects humans in the image, which are then cropped. The crops are resized and fed into the pose detection model. This model outputs a heat map for each key point, trained using mean-squared error loss. The model leverages a new dataset with 1 million manually annotated images, capturing 308 key points. It is then evaluated on 114 key points that are in common with Coco whole body. Sapiens 2B significantly improves the state-of-the-art, beating the prior art by 7.6 AP. The dense prediction tasks, body part segmentation, depth estimation, and surface normal prediction share a common decoder architecture, with variations in the number of output channels. Let's explore each task briefly. Body part segmentation is extended from 20 classes to 28 classes, adding finer distinctions like upper and lower halves of limbs and new head classes, upper and lower lips, teeth, and tongue. The model is trained on 100,000 annotated images using a weighted cross-entropy. Table 4 shows comparison of Sapiens model with existing body part segmentation methods fine-tuned on the new train set. Even the smallest model, Sapiens 0.3b, outperforms previous methods. Depth estimation uses a synthetic dataset generated using 600 high-resolution photogrammetry human scans. For each image, a random background is selected from 100 environment maps, and a virtual camera with random parameters is set within a scene to generate the images. The model predicts normalized depth, and it is trained by minimizing the depth loss, which is calculated only for human pixels, ignoring the rest of the image. The model is evaluated on T-Human 2.0 and Hi4D datasets. Table 5 shows comparisons with current state-of-the-art methods. Delta 1 metric doesn't effectively reflect performance in human scenes due to the small depth variations, so root mean squared error is reported as a more informative metric. While baseline models are trained on a variety of scenes, Sapiens specializes in human-centric depth estimation and shows great generalization performance, outperforming baseline models. The surface normal prediction model is trained and evaluated on the same datasets as depth estimator, and the loss is also calculated only on human pixels. In Table 6, we see that Sapiens again beats the previous state-of-the-art on both datasets, and qualitative analysis shows that it also predicts more detailed and smoother surfaces. To evaluate the impact of pre-training on human-centric datasets, the authors compared results to pre-training on general datasets. To create general datasets, 100 million and 300 million general images are randomly sampled from the 1 billion image corpus to create the general 100M and general 300M datasets respectively. Models pre-trained on human-centric datasets consistently outperform models pre-trained on general datasets across all tasks for both dataset sizes. Additionally, the number of unique human images in pre-training strongly correlates with better downstream performance. This graph shows the impact on surface normal prediction performance of Sapiens 0.3b. Despite limited background variation and only third-person views in the training, Sapiens generalizes impressively to multi-person images, different ages, and diverse viewpoints. In summary, Sapiens models establish new state-of-the-art benchmarks across multiple human-centric tasks. However, they face challenges in handling rare poses, crowded scenes, and severe occlusions. The paper's code and pre-trained models are publicly available on GitHub, so check it out if you're interested. And if you found this explanation helpful, please like the video and subscribe to the channel. Let me know in the comments if you have suggestions for future papers you'd like me to cover. Thanks for watching and see you in the next video.